So thanks for having me here today. I actually had a harried travel schedule yesterday because the plane wouldn't land in Urbana, so we had to fly back to Chicago, and I ended up driving with a bunch of random people down here. It was fun, but I knew I got to the right place finally at the end of the day because I looked at the hotel, I looked at the menu in the hotel and the shower curtain, and I saw graphene. So when I looked at it, large scale graphene on plastic. Okay, so basically we work on two areas in my group that I'm going to talk about both of them today. One of them has to do with sensing, implementing materials. All of these are nanotechnology enabled. I'll explain what that means as we go on, but basically it's actually utilizing the additional performance that nanoscale materials may provide that bulk or even microscale materials may not have. And basically exploiting those properties and then implementing them in interesting form factors, for example, for sensing in implantable applications, or also potentially energy harvesting, for example, being able to implement some sort of energy harvester that's connected with your body somehow that can charge an implantable device. So we're interested, I look at materials, the whole gamut from fabrication, synthesis of materials, to the characterization, fundamental characterization, to the device applications. And we usually stop there. We don't do a whole lot of manufacturing. I think that's where you guys are experts. So maybe you can take some of these ideas and put them into larger scale things later on. But so the first part of my talk is some stuff that I'm really excited about. Actually, this paper just got accepted to Nature Communications today, so I'm really excited. Our first bona fide Nature whatever paper. So not that that means anything, but I'm excited. So the first thing I want to talk about today, this topic that I've been interested in for a while, and of course I'm coming at this from somewhat right field because I didn't know anything about bacteria 2 years ago, and now I know a fair amount about it. But basically this concept that we have all these problems in this country. If you hear about E. coli contamination, people getting sick from bacteria, and you have to wonder why that is, because in developing countries, you would think this would be a problem in developing countries where the water supply is poor, so that's why they have bacterial contamination there. So the question is, why does this happen also in developed countries? Why is this such a serious problem? And the answer is because we consume foods like the richer the country gets, the more meat and dairy it consumes, and those products tend to have high bacterial contamination on them because they're animal species. And the problem with bacteria is that all it takes is one or a few cells to make you sick. Okay, that's called minimum effective dose, the MID. So basically the MID is so small in these bacteria that you need a way of detecting them at very low cellular levels. For example, on the single cell to 10 cell level. And the only way to reliably do that now is to use a technique called ELISA, or to use PCR analysis, where you take a sample and then send it away to a lab and test it. So what we'd like to do is be able to actually do this kind of testing directly on the source of these problems, which is human contamination, food contamination, water contamination, and really implement these devices directly on those sources. Okay, so these are the challenges and where we'd like to go with this. So of course we had to pick some sort of material to do that, and this is where the nano comes into play. First of all, the nice thing about graphene, every atom is a surface atom, and so as a sensor, it acts as a very good sensor because every atom is a surface atom, so anything that binds to the graphene is going to modulate its conductance. But second of all, from a mechanical standpoint, because it's a monolayer material, basically a single atom material, there's a high adhesive energy between graphene and any kind of substrate. In fact, it acts somewhat like a liquid solid interface. So this interface means that you can basically interface it with any material and be able to, including food or the body, and it will stick there pretty well, right? And of course, the other thing about graphene from a mechanical standpoint is it has one of the highest mechanical moduli, 1 terapascal. And so that means that, again, it's a robust material that you can implement on a variety of platforms, including, for example, teeth, bone, skin, things like that. So the question is, how do you do that? And of course, we all know graphene can be transfer printed. That's how they isolated graphene in the first place in 2004. But the way we decided to do it in this work is we took some inspiration from John Rogers' work, and we used this guy here. This is a silk moth, which, by the way, these are like dogs, right? They didn't develop naturally as silk moths, just like the dogs didn't really develop as dogs. They basically, through human intervention, using silk as a clothing material, we basically influence their development. But if you wet the silk a little bit, you can process the silk either in terms of alpha helices, which is water soluble, or beta sheets, which is insoluble. In the water soluble form, if you wet it a little bit, this is work we did in collaboration with Fio Almanetto at Tufts. If you wet it a little bit, you can actually print the graphene onto this silk platform here. You can print it multiple times, and it looks, of course, like someone scribbled with a pencil on the silk, because graphene is, of course, part of graphite, which is what your pencil lead is. So you can print this graphene onto any kind of substrate. Again, the high adhesive energy there. And so we had this idea that if you can do that, then you can basically build some sort of device on it that you can then dissolve the silk away and transfer that entire device onto a platform. So the device looks something like this. You have contacts which make contact with the graphene, electrical contact. And then we have maybe this wireless coil here, so you can get wireless readout, remote powering of the device, let's say on a tooth or something like that. I'll explain why a tooth here. So the reason why we chose a tooth for this work is because teeth are interesting because they come in contact with both saliva and breath. So there's a lot of different things we can do with this platform, but I'll show you, it doesn't necessarily need to be a tooth. If you look at tooth enamel, it's a very rugged surface, and it's of course made up of hydroxyapatite, but it's made up of more than just that, because if you take a nanoindentor probe and probe into the tooth, it's not that it doesn't, you can actually indent it to some extent. It doesn't fracture the way that, you can see this is the stress strain curve for hydroxyapatite. I'm in a mechanical engineering department, so I learned to love these things. But basically, if you look at the actual tooth stress strain curve here, you can see it's a tougher material. It doesn't fracture the way that hydroxyapatite does. And of course, the reason for that is because tooth isn't just hydroxyapatite, it also contains proteins. And these proteins confer some toughness on the tooth. And basically, you have this rugged surface, which is a biomaterial. And so it's an interesting surface to work with. It comes in contact with saliva and breath, as I mentioned before. So this was taken from the Journal of Dentistry. I didn't realize I'd be reading from that type of journal before I started this project. But anyway, so this I thought would be an interesting platform to work with. And so Fio Almanetto gave us one of his teeth. And I have no idea why he had it available. We put $1 under his pillow after we got it. But basically, we took his tooth here, and we printed this graphene onto the tooth. And you can see here, here's the graphene with electrodes here. And you can do Raman spectroscopy on that tooth. In fact, the teeth peaks in the Raman spectrum are distinct from the graphene peaks. So you can see clearly the monolayer graphene 2D and G peaks there on the tooth. But of course, this doesn't have the wireless coil on it. Which the problem with the wireless coil is that we couldn't find a good way yet of miniaturizing it. So it actually added a fair amount of space to this overall device here. So instead of a human tooth, we live in farmland just like you guys do. And so I had an undergrad go in the middle of the night and steal a cow tooth from the local farm so we could fit this device on the cow tooth. Also, we put $1 under the cow's pillow. This research costs a lot of money, as you can tell. Of course, you can also print it onto a chicken breast, as you can see here. That one we actually bought in the store. And because cheese actually was recently Costco cheese was a big source of E. coli contamination, so we got specifically Costco cheese and printed the device on there. And also another big source of bacterial contamination is in hospitals. MRSA is a big problem, so we printed it onto IV bags and things like that. MRSA is staph bacteria, which basically has developed a resistance to penicillin, and it hangs around on hospital shower curtains and on IV bags and even doctors' ties. It can live under dry conditions for a long time. That caused a lot of people to be sick. And I'll talk about that later. Okay, so we've been able to implement this device on a variety of platforms. The next question you can ask is, well, what about the stability of it? So we took the IV bag, we crumpled it up, we put it in water, and the device pretty much holds up. We also took the cow tooth, put it in Listerine, and swirled it up and sonicated it. As you can see here, that's the tooth being sonicated. If you take it out and then do the Raman spectrum after that, you do see that there's an increase in the D peak here on the graphene. And part of the reason for that is because that D peak actually represents is actually graphene edges. So we probably are, not through this process, but through the sonication process, we are probably creating more graphene edges there when we sonicate this guy up. And so there probably are some more defects here, although that may not necessarily be a bad thing in graphene because it's a semi-metal. So it may be a way of opening up a band gap in the graphene. Okay, so we have this platform now. We can see it's reasonably robust. So the next question to ask is, well, what's the sensitivity of this platform? And then also, how do we tailor it for bacteria sources? So the first question is easy to answer. We can just look at the sensitivity of this graphene platform toward bacteria. And if we play this movie right here, this is just bare graphene here. You can see we're actually focused in on the plane of the graphene, and then this bacteria binds. There, right there, bound. This we fluorescently labeled the bacteria, so we can monitor it optically while we monitor the electrical properties of the graphene. And you can see as soon as it bound there, you actually get this distinct 1% change in the graphene conductance there. And then after the bacteria unbinds, it goes away. It goes back up to the baseline. So that means that the resolution of this device, we can see it by doing this simultaneous optical and electrical measurement, is the single bacterial level that you need in order to combat bacterial infection, right? That minimum effective dose that I talked about earlier. So that's good. Sensitivity is the best you can get, single cell level. But the next question is, how do you modify the graphene so that it can bind only bacteria and nothing else, or maybe even distinguish between different bacteria? So this is a much more difficult problem. And the answer is, we still don't have a great answer, but we have one answer for it. But this is a generic platform, so there may be better things that come down the line. So, but I'll just tell you about what we did here. So the obvious way, the way that people first think about is to use antibodies to do that. So antibodies are very highly selective. They can bind anything, including bacteria. But the problem with the antibody is it's an intricately folded protein structure. So if you put it on a surface, it's going to denature fairly quickly, and the device is not going to be useful at that point. So I don't think of antibodies as the best way to go here. Another option is to use something like RNA, aptamer here. And the problem with that is that RNA is basically only 4 base pairs, A, C, T, and G, that you then form into this aptamer structure. And it can reach reasonably high selectivity, but what you'd really want to do is use a biomolecule that most mimics what they do in proteins. Proteins are made up of amino acids, not nucleic acids, right? So what we ended up using are peptides here. And of course, there's disadvantages of peptides. I'm going to get into this story as we go along here. But we decided to use peptides because they're the closest analog to antibodies without having the kind of problems with denaturing that antibodies have. Although they have their own distinct drawbacks. We're going to talk about that as in here. Okay. So first question is, well, we need a peptide that's going to bind to bacteria. We know that. But we're also going to need a peptide that's going to bind to the graphene as well. And we're going to have to link those peptides together. So the first thing we had to do is find out which peptides are going to bind to graphene. And the approach we use to do this is an approach called phage display, where you basically buy this kit of literally 1 billion viruses. These viruses called phage, which infect bacteria. And each phage, at the terminal point of the phage, has this peptide on it. You can see by these different shapes, where each completely different peptide sequence on it, randomly generated sequence here. And you can then take these phage and throw it at your target, in our case graphene, see which one it binds and what don't bind. And then you can go back and figure out what those peptide sequences that bind, and say those are binders to your target, okay? In fact, recently, this was a paper we did. It took us a lot of effort. It didn't really get much press interest or general interest anywhere, but I thought it was cool. Where we basically were able to actually automate this entire phage display process in a microfluidic chip. And in fact, we can reduce the time about 16-fold in this phage display process by miniaturizing it like this. If you're interested in that, we could talk about that later. So the problem with graphene is you don't necessarily want to covalently modify the graphene, because if you do, you're actually going to have to break the bonds in the graphene to do that. And that's going to actually lead to changes in the graphene properties. For example, the electronic properties, which we don't necessarily want to modify. We want to keep them so that we can keep that single bacterial resolution. So this phage display is a perfect approach for this, because you can generate peptide sequences that non-covalently bind to the graphene. So this lunar landing picture that we have here, this is a representation of what the phage display process looks like. You throw, again, these phage at some sort of substrate. In this case, it would be graphene, or it could be graphite or graphene on another substrate. And then that way you can identify peptides that actually bind to your target, to the graphene. So you're probably wondering, well, can you really get selective peptides that way? So we got some really interesting results that I wasn't expecting, which is that some of these peptides, this GBP right here, this is a peptide. We did some AFM experiments and some modeling here. It actually has this terminal, this is the sequence down here, it has this terminal glutamate there. It's negatively charged at neutral pH, so it actually will bind to the positively charged edge, the hydrogen terminated edge of the graphene here. So it will actually go toward the graphene edges. So if you look at this graphene sheet here, you can see the peptides actually line up exactly along the graphene graphite edges there, which I thought was pretty cool. You can also generate peptides in this process that actually cover the entire sheet of the graphene. So these are planar binding peptides here that cover the entire graphene sheet there. We can do modeling that show that because it has a lot of aromatic rings, they actually pi stack with the graphene, they'll actually laminate across the entire sheet of the graphene. So these peptides actually do different things. They can either bind to the edges or to planes based on their chemistry, which was pretty cool. And we can also pattern the graphene in interesting ways in order to make a nanoscale material and then to see what the binding looks like. So we developed this approach which we call photolithography and etching for nanoscale lithography that we call pencil, because all these things need some sort of acronym. And basically the way this works is you just coat a wafer with nickel, and then you do standard microlithography on that wafer, and you undercut etch the nickel. And actually you can etch it down to pretty significantly small features. For example, here's nickel that we patterned down to like the 30 nanometer level using this pencil approach. And of course, since the photolithography is the base of this approach, you can do it over an entire wafer. So if you hold the wafer up to sunlight, you'll actually diffract the natural sunlight there. You can see it with these nanowires patterned over the whole wafer. So the point here is that if you have graphene underneath that nickel layer in the first place, you can then translate those nickel nanowires into the graphene underneath and form nanoscale graphene. So this is what it looks like here with the nickel patterned here, and underneath each of these nickel nanowires here is actually a nanoscale graphene. Okay, and the background is a silicon wafer. So this picture doesn't show you, but we actually took this system here and then exposed those phage with the graphene peptide binders to this wafer here. And you can see you don't see any phage in this picture, but if you etch away that nickel, expose those graphene nanostrips, you see something which I thought was pretty amazing, which is that these phage actually line up perfectly along those graphene strips there, which means that they bind to graphene and not nickel, and they bind to graphene and not the background silicon wafer. So there is some degree of selectivity that these peptides do provide using this phage display process. Okay? So that gives us one end of the thing. We have a peptide which binds to graphene. But now we need some sort of system peptide that's going to bind to bacteria. Okay, so how do we do this? Well, what you can do is this is all synthesized in the lab. You can just synthesize a single peptide which has one functional group on one side and another one on the other side. So these are peptides here which bind to some material on one side, and then you can, let's say, bind gold nanoparticles on the other side. So we did that, and you can see here these gold nanoparticles with the edge binding peptides, they actually line up exactly along those edges, these gold nanoparticles here, because of this bifunctional peptide. We call it bifunctional peptide. So it has one moiety on one end, another one on the other end, so you can bind two different things in one single step using a single peptide system. Okay, so we tested this out in a sensor platform. We actually took, actually you can train bees to detect TNT. I don't know if you know this, but you can train them so that every time they sense TNT, they'll stick out their proboscis, which is their tongue here, this thing here. In fact, people tried to start a company where they put these things in airports to detect TNT, but the problem is the bees always flew away. Okay, so what would be much better is to have some sort of device that can do this same thing. And you can actually go into the honeybee's olfactory receptor protein and see exactly where the TNT is binding. You can take that peptide sequence and again create a bifunctional peptide that binds graphene on one end and TNT on the other without harming any bees in the process. So you can see here the bare graphene doesn't respond much to TNT. That's the black line up here. When you add in this peptide here that binds to TNT on one end and graphene on the other, you then get this response to parts per billion levels of TNT here. Okay. So this is just a demonstration that we can do TNT binding here. But again, what we really want to do is we want to target bacteria. Although again, this is a generic platform that can be used for any type of system. Okay, so this is where I'm going to tell you a little bit of a story as we continue our animal theme here. And the story goes like this, which is we mentioned before that the peptides are not very selective, the way antibodies are selective. So the question is, how does the pharmaceutical industry now detect bacterial contamination on its products. Let's say on drugs, to make sure they're not contaminated with bacteria, or on some sort of implantable device to make sure they don't implant something in you that has some bacterial contamination. And I didn't know this until I started watching Nova about a year ago. I can't afford to pay for cable, so I just watched Nova. And they had this whole story here which I was fascinated about. And it turns out what they do is they go to the Delaware Bay, which is by me, and they collect in a boat, they collect all these horseshoe crabs in the boat. And they take these horseshoe crabs and they mount them in the lab, and they basically drain them of their blood here, which happens to be blue because it has hemocyanin in it. Okay? And then they, after they've drained their blood, they throw the horseshoe crab back in the water, but of course some of them die during this process. And this story was about the horseshoe crabs dying out, partly because of this process here. So the question is, this is the state of the art, by the way. They used to actually take rabbits and inject them with their drugs to see, and then they'd have to wait to see if the rabbit got sick, to see if it was contaminated with bacteria, but that took too long. So the horseshoe crab method is faster. This is actually called the LAL test. They can take this blood and then put it on their product, and right away they'll see if there's a coagulation of the blood. And the question is, why does this happen? The reason is because these horseshoe crabs, they live in an aquatic environment, right? Aquatic environments are surrounded by bacteria. And so the horseshoe crab needs a very efficient way of defending itself against bacteria. So what it does is the blood actually will coagulate around any bacteria that it comes in contact with, and it'll force that bacteria in place, and then it'll come in and kill the bacteria in the blood system with antibodies and peptides. So the point of this, the reason why I'm telling you this is because this blood here, this whole process here is not highly selective, right? You can't distinguish one bacteria from another by doing this. You just want to know generally if your system is contaminated with bacteria. And that's actually what we want to do here. So what we do here is we look at it. This is a happy frog couple. These are called African cloud frogs. And on their skin, again, these are aquatic frogs. And on their skin are peptides. And they're called antimicrobial peptides, which basically defend the frog against any kind of bacterial contamination, because they act as a first line of defense, and a general first line of defense. They're not as selective as antibodies, but they are robust things that can be on the surface of your skin without denaturing, and can bind to bacteria that the frog has maybe never seen before, bind to the skin and be killed by this antimicrobial peptide on the frog's skin. So this we thought was an interesting approach here, to take these peptides and look at them. So we took these peptides, these antimicrobial peptides. They're basically, they sequester electrostatic regions. So they have cationic regions which actually target the LPS layer of the bacteria, which is negatively charged. So they basically, that's how they kill the bacteria there. In fact, animals like erythrocyte cells, red blood cells, all of our negative charges are on the inner leaflet of the cell. So we actually aren't affected by antimicrobial peptides. We actually have them in our eyes to protect our eyes from infection. So basically we're protected from antimicrobial peptides, and the bacteria cannot re-engineer its cell wall to protect against them either. So it actually can't form a resistance to them. So it's a nice little system to work with here. These we call them AMPs. Okay. So we can make a single peptide here which binds graphene on one end and has an antimicrobial peptide on the other end. And this is what it looks like. You can see here's our graphene binding peptide. You can see the aromatic rings there, the pi stacked with the graphene. Here's a linker that links them together, and there's the antimicrobial peptide on the other side. So we basically just self-assemble that onto some graphene surface, and this is the response we get. So you can see that the bare graphene here doesn't. Sorry, this is a graphene binding peptide here. It doesn't respond to MRSA bacteria here. Only when we add in the AMP with the graphene binding peptide there do we actually get a response to the bacteria. And you can see red blood cells here also don't. They actually, when you elute with water, they go back to the baseline. So we actually can distinguish bacterial cells from red blood cells using this antimicrobial sensing system here. So that's good. But of course, the next thing we want to do is make this wireless. So we have these antimicrobial peptides. We actually found some of them that bind to H. pylori, which, again, we talked about the tooth before. H. pylori is something that occurs in your saliva, which tells you if you have stomach cancers or stomach ulcer, either one. So we decided to implement those peptides on this tooth, this cow tooth here. And we had this wireless coil that we put on top of the tooth so we can get wireless readout. And you can see here, I'll show you a video in a second, but you can see that in saliva, if you just have bare saliva, that you don't get a response But if you add the H. pylori bacteria on top of that, you can see a quite significant response. This is all wireless now. And you can actually go down to the 1 bacteria per microliter, actually the 100 bacteria per milliliter level, which is below the minimum effective dose of H. pylori. This is all a wireless system. And so one of the things we're interested in now is actually doing this in a breath type of system. So we have our tooth here, and I'll show you what this looks like. So we have a baseline conductance here. Here's the tooth, the cow tooth. There's the coil on it. You can see the tooth isn't connected to anything. It's just standing there freestanding. We have this baseline here, and then my student comes in, Manu, and he breathes on the tooth. And you can see by breathing on the tooth, the conductance goes up quite significantly. And it stays up there for a second, then the molecules from his breath desorb, and it comes back down to the baseline conductance right there. And then so my student comes in, Manu, and he breathes on the tooth again, freestanding tooth, and it goes back up again, okay? So I thought it was cool. But you can actually, we have a project now with the American Asthma Foundation where we're actually trying to see if we can distinguish asthma breath from regular breath using this approach. Because asthma is a huge problem in cows, in case you didn't know that. So, okay. So this is the first part of my talk. Then the second part of my talk has to do with the energy harvesting that we've been doing a lot of work in here, nanoscale piezoelectrics. And the inspiration for this part of the talk was we had this idea a couple years ago that if you could actually harness, let's say, lung motion to power some implantable device, that would be very convenient. Because it turns out that implantable devices now run off of batteries, like pacemakers. And the problem is every 5 to 10 years, this battery dies, just like your cell phone battery dies. But the problem is it's inside your body. So you actually need to have a surgery to replace this entire pacemaker system. And in fact, that can lead to infection. And also, it's extremely inconvenient and costly, too. And so we had this idea, maybe you can actually use internal energy to prolong the battery life of that pacemaker and kind of prevent this problem. And you can think of this as a problem where alternative energy sources would not be useful, because you can think maybe if you have a solar cell to do that, but then you need a solar panel on your chest and you have to wear shirts with holes in it all the time. So we thought maybe you can use lung motion or some sort of motion power to do that. And if you look at, actually, we eat 2,000 calories per day. So that's 100 watts that can be dissipated. And most of that is actually dissipated through walking, okay? Which is about 70 watts of power available. And then some of it is also dissipated by lungs, about 1 watt. This is ideal calculations here. So if you think about what a pacemaker requires, it's actually on the order of microwatt to milliwatt range, okay? Especially when it's idle. So this is not totally incompatible with the energy requirements of a pacemaker. But you need to be able to harness it as efficiently as possible. Okay, so efficiency is a key thing. So the way we do this in this project, we use a material called a piezoelectric, which is basically a crystal that when you mechanically deform this crystal, you actually get a shifting of the anions relative to the cations in the crystal here. And that basically leads to a polarization on the crystal, which basically means you're converting mechanical energy into electrical energy. And of course, you can do this in reverse and get actuators. So in fact, some acoustic electric guitars have a piezoelectric microphone in them where you play the strings vibrate, so that vibrates the crystal, and you get electrical readout. And you can also make speakers out of them too, piezo speakers. Okay. And if you look at the materials that are available to use in this kind of project, there's basically you have to look at the governing equations here. So you have to look at how much energy is stored in these piezoelectric crystals. And basically it's determined by 3 things. The first thing is the volume of the piezo, this AT here, the area, cross-sectional area by the thickness. So the more volume of piezo you have, the more power you're going to be able to generate. Okay, that's one part of the equation. The second thing is the applied stress, this F over A term here. So the harder you stress these materials, the more power they're going to be able to generate. So that doesn't really tell you, neither of those tells you much about material selection. The thing that matters in material selection is this D constant here, this piezoelectric charge constant, which is intrinsic to the material and gives you an idea, a parameter, part of the material that tells you how efficiently you can convert energy in these materials. And in fact, the efficiency, this K value, also depends directly on that D value there. It's a tensor, so that's why you have this 3,3 at the bottom. So if you look at the materials available to you, so one of them is actually the bone in your body is very weakly piezoelectric. But it'd be difficult to put wires all over your bone and harness that into an iPod or something like that. Second thing is naturally occurring materials, quartz. which is piezoelectric too. The tetrahedron is actually a piezoelectric system. But again, it's a very weak coupling. The D value is quite low. PVDF is a polymer that's piezoelectric. And zinc oxide, you've heard a lot about zinc oxide. It's actually a piezoelectric, but it's not any better than PVDF as a piezoelectric, turns out. But the one material that is PZT, which actually has a piezoelectric charge constant about 10 times that of zinc oxide and PVDF. So it's actually 10 times more efficient at converting power between electrical energy and mechanical energy. In fact, it can be up to 80% efficient. So this is the perfect material to, if one wants to create an energy harvesting system, it seems like the perfect material to use, but of course it's a hard, brittle material, and it has lead in it, which is not biocompatible. So there's some problems there too, and this is where we use nanotechnology to get around that. So actually, my interest in this is partly that, but also the very first research, this is me in 1998. I was slightly more socially awkward back then, this was the very first project I worked on when I was did an NSFRU after my sophomore year in college at UPenn, and I worked with this guy named Andy Rapp who does theoretical calculations. So I actually did DFT calculations. This was my result here at the end of the summer on PZT here. This is the you have lead here. It's a perovskite structure, so you have lead, oxygen at the corners, and then you have a titanium or zirconium atom at the center there. And we actually looked at how the charge density changes as you move these atoms around in the crystal there. So that was a fun little project. But more recently, I've been interested in PZT for the reasons I mentioned before, but also because it's actually very difficult to make nanowires out of PZT. So basically, these days, nanowires have been made out of pretty much any material except for PZT and materials like that. And the reason is because you can't do the kind of VLS approach that you normally do with growing nanowires, because you can't get a catalyst that can solubilize lead, zirconium, titanium, all these different components of PZT, and then grow them in idealized ways. So the first one was a paper by Changwu Zhao at USC where he grew magnesium oxide templates using VLS and then deposited PZT on top of it. You can use confined templates, these Illumina templates, but you're going to get polycrystalline PZT, which is going to lower your D33 value. Or you can also use hydrothermal approaches, but it's difficult to get the correct stoichiometry, which you need in PZT to get the highest D value. So what we did in our case is we started with a thin film, because there's been decades of research on growing nice crystalline stoichiometric thin films of PZT, and then we carve it up into nanoscale structures that you can see here. The magnesium oxide is a lattice match, or closest lattice match with PZT that we can find. So if you take this wafer and then dissolve the wafer, this is very obviously inspired by John Rogers here, except in our case we're dissolving the entire wafer here. So we can dissolve the entire wafer and print this just like you print newspaper ink on a silly putty onto this silicone platform here, which of course is biocompatible platform, and silicone is used in cosmetic implants, right? And of course you can do this, and just like you guys do with silicon there, you can do it over large areas just like you can do with silicon. This is the outline of the wafer there with high yield. So this is totally inspired by John Rogers' approach, this kind of transfer printing method. But now we have this PZT material on a biocompatible interface, right? And also the PZT here is very thin. It's nanometer, they're nanoribbons, and so that actually confers more flexibility to them than you would get in a bulk scale PZT, which is not very flexible at all. So the first question is the PZT still high performance when you transfer onto the ribbon? And the way that we measured it is this approach called piezo force microscopy, which is just like AFM, which you guys probably know about, but instead the tip is conducting. So you put this conducting tip down on your PZT, you have to have a back electrode, you apply an AC voltage between the tip and the back, and the PZT will basically strain like it's supposed to do. And the ratio between the applied voltage and the strain there actually gives you your D33 value directly. So of course this was on PDMS. PDMS is not conducting, so our trick was we actually doped the PDMS with carbon here, and then put the tip there between the PDMS conducting part and then the top of the ribbon there. And we actually got pretty good D values, actually on the order of 100 here, as you can see here. So not the kind of 250 that the bulk PZT is, but there's a reason for that. In thin films of PZT, you're actually dampened slightly by the substrate. In the bulk scale, there's no damping effect here, okay? Now, of course, you can make lots of cool devices from this. You can actually make interdigitated electrodes here that if you pull them correctly, you'll actually access that D33 mode, which is the most efficient mode here. So we can do this over large areas. We're not really a manufacturing group. This is not something we normally do. I consider this your guys' expertise. But you can actually make little generators here with voltages, let's say, on the order of a few volts, and the current, of course, is much lower because you're actually generating a cationic displacement rather than electron displacement. But you can see right here.
This is an electrical current, and it's flat right now. But when I tap on this piece of PVT in printed plastic, the lines actually go up and down. That means I'm creating electricity just by tapping on the piece.
That was a former postdoc of my group. So she didn't last very long, but she actually got good data. So we actually can get up to, if you normalize it by the area there, or by the volume, of course, you can actually get up to 10 milliwatt per cubic centimeter. But of course, the absolute power being generated here is on the order of let's say, microwatt or sub-microwatt. So we still have a lot of work to do there, although again, that's not really what we try to focus on. We just don't have the kind of capabilities that you have. So we like to do other cool stuff that we think is cool. So one of them has to do with, if you implement this on, let's say, your lung or some sort of tissue, then you need a way to make it flexible, not just flexible like your water bottle, but also stretchable too. In fact, PVDF, that piezoelectric polymer PVDF, is not very stretchable. It's more of like a plastic type of polymer. So there's actually been no stretchable piezoelectrics that have been made up to this point. So the first thing we did is we took our chip and put it under the SEM and see what happens if you stretch it. And you can't strain it very far before you start to see little cracks breaking. And if you listen closely to the SEM, it sounds a little bit like Rice Krispies while you do this, as this thing like breaks up on the surface. So what we had this, of course, again, another idea inspired by John Rogers. But in fact, before there was John Rogers, there was paint and balloons. So if you take a balloon and paint it with a stiff paint material here, and then compress the balloon, you actually form a buckling pattern on the balloon. There's lots of people who spend a lot of time studying these buckles here. And in fact, the way you do it, you can actually generate interesting modes where you have a low order frequency buckling here on top of a high order buckling there. So it's actually an interesting platform here. And this is called constrained Euler buckling. So it's Euler buckling with a constraint, which is the balloon here. So before there were paint on balloons, there were some faculty in my department who actually studied this, were the first people to study this constrained Euler buckling here. So what they did is they actually buckled this thin foil here. This was done by Phil Holmes and Barry Royce, who are senior members of my department here. 1997, they had this buckle here where they put little two constraints on it. He actually still has this little contraption in his office. And you can actually, by using your finger, you can switch between different buckling modes, different Euler buckling modes here, between these two constraints here, okay? So it's an interesting problem, this constrained Euler buckling. Of course, in our case, we did the John Rogers trick, where we basically stretch our PDMS down and then print it onto the PZT here and then release. So you can get these buckles here. Of course, PZT has a weird surface chemistry. So we can't do the same things that you guys do. We have to use other tricks, like, for example, patterning the PDMS here in order to get the buckles to be in phase with each other rather than out of phase, okay? But we can't actually do this, because again, the PZT is so thin, even though the Young's modulus is so high, you can't actually get these buckles to form in PZT. So now when you stretch it under the SEM, instead of it cracking up on the surface, you'll see that actually will flatten down nicely onto the substrate, up to about a 10% stretching, and then you can release it and it'll buckle back up. And so in our case, this is interesting because, again, no stretchable piezoelectric has ever been made. And also because as you do that, as you stretch it out, you're actually deforming the crystal. So you should be able to generate power that way. And in fact, we did. If you put silver paint at the end here and you stretch this thing out, here's our buckled ribbons here, you actually will generate little spikes of power as you do it. And just to prove that this is from the ribbons and not from the electrodes, we can actually do 5 ribbons here or 10 ribbons here. You can see you get double the current as you add more ribbons to the system. So you can generate power in this kind of stretching mode. But what we thought was incredibly fascinating as we did this, something that we were somewhat surprised about, is we looked at the actual what's going on in the ribbon locally using our piezo, our PFM probe, this piezo force microscopy probe. And you can probe, it's a nanometer probe, so you can probe the top of the ribbon and you can probe the flat part of the same ribbon. So here's the AFM image of what that buckle looks like. And we wanted to see if there are any differences in the piezo response at the buckle versus the flat part. Okay, and we saw this really cool result here, where you actually can see as you go from the flat part of the ribbon up to the buckle, you actually get a 50% enhancement in the D33 value. Okay, so you actually get an enhanced piezoelectric charge constant due to this buckling of the ribbon. Okay, here's a calculation of the strain gradient as you go along the ribbon there. This is the profile of the buckle there. So one of the things we've been studying a lot these days is trying to figure out where does this increased piezoelectric response come from. Okay, there's basically two things that we can think of. The first thing is that the buckle is off. It's not on the substrate. Okay, it actually comes off of the substrate, and so as a result, it's not clamped by the substrate underneath. It's not damped. The substrate is basically this elastomer, so it acts as a damping force or damping energy. So the first thing is we looked in literature. We actually saw that in clamped PZT, this is from 2004, clamped PZT, you actually get significantly reduced piezoelectric charge constant compared to freestanding PZT because of this clamping effect. And in fact, this is why bulk PZT has a higher piezoelectric charge constant than thin film PZT. So that's one explanation. I think this is the least interesting explanation. Another explanation, which I think is incredibly fascinating, which I'm going to talk about here for the rest of our time here, is this concept called flexoelectricity, the flexoelectric effect, which basically means when you take a wafer and you bend it, you basically form an expansion strain at the top and a compressive strain underneath. Okay, so you actually can create a polarization. This was work that was pioneered by Eric Cross at Penn State. You can create a polarization just by bending a material. So if you look at the equations here, the first part is our D constant that we talked about before, which is proportional to strain. But this flexoelectric contribution is proportional to this strain gradient, okay, going from expansion to compression in this buckle part. And in our case, our strain gradients are enormous because these are nanoscale buckles here. In fact, there's even some interest by some people in generating materials which have a 0 D value and just look like piezoelectric materials, but they're not actually piezoelectric materials just by this flexoelectric effect. Here, for example, here's a salt crystal here. And as you buckle it, you can actually see that this buckling changes the symmetry. It actually gets rid of the centrosymmetric symmetry of the salt crystal. So you can actually generate polarization by this flexoelectric effect here. I just think it's incredibly fascinating. And of course, it scales with nanometer scale. As you go down to nanometer scales, you actually get a bigger response. Okay, so I have a question for you guys. Is there another system that you can think about that looks constrained like this or has like a high curvature and has a polarization associated with it? Say it. Someone said it. Okay, cell membrane, good. Okay, so we looked in literature. There's not been a whole lot of work on flexoelectricity, but we looked in the literature and we found that there was this group which proposed that flexoelectricity is the reason that we can hear, okay? So they actually modeled this stereocilia, this hair cell in your ear, and they said, well, the amplification that you hear, the usual way of thinking about hearing actually cannot be explained just by the usual system alone, where your hair cell vibrates due to acoustic waves and you get a depolarization. What they think is going on is this depolarization across the membrane is actually creating this inverse flexoelectric effect. So the depolarization is actually changing the strain gradient of that membrane, and it's actually amplifying that signal in your ear. And they think that as you get older, you're actually losing you're losing your hearing because you're losing your flexoelectric abilities, believe it or not. Who knows? But there's been some work also at Oak Ridge where they actually looked at tobacco mosaic viruses. They can actually probe the piezo response in these tobacco mosaic viruses, and they can see that there is a flexoelectric effect of about 10 picometer per volt, okay, which is, I think, fascinating. But we had this idea of maybe you can actually measure this flexoelectric effect in cells using our piezoelectric nanoribbons. And if you look at what people have done in the past, they've actually been able to take AFM probes and probe them into cells and depolarize the cells here. And it's just like when you have clothes on a clothesline, right? If you change the tension on the clothesline, the clothes are going to go up, right? The whole thing is going to go up, so the clothes are going to go up. So if you had a probe here, an AFM probe at the top of your clothesline, it would go up based on changing that tension. So the tension is changed by polarizing the cell, okay? That's the flexoelectric effect. And you can see it here. Here's the response here. You can see that most cells change on the order of, let's say, a nanometer. Very small amount due to this flexoelectric effect as you polarize the cell. So they're using a patch clamp here to polarize it and the AFM to measure that displacement. So we thought, well, maybe there's a way we can do that with our system. Maybe there's a way we can couple, let's say, neurons, which people have studied a little bit, but not very much, this flexoelectric effect, and see if you can put a neuron on a piezo ribbon and then polarize the neuron, and then see if it expands, which should then push the piezo ribbon down and then generate a voltage across the ribbon here. So basically measuring not the electrical component of neurons, which everyone knows about electronic signaling in neurons, but not very many people know about mechanics in neurons. It's a whole different ballgame. Okay? We know there's mechanics associated with creating new synapses and elongation of dendrites and axons, but people haven't studied it that much. So we wanted to study it with our piezo ribbons here. So we did this nice work. My student actually created these nice, beautiful PZT nanocantilevers and then cultured these neuron cells on them. I have no idea how he learned to do this because I've never done neuron stuff before. But he actually cultured these neurons on the cell to see what the response would be. And of course, the first question you could ask is, do neurons grow on PZT? It has lead, right? So I was surprised, again, we did some viability studies on this system. You can see here that neurons like to, even though neurons, they actually love to die, right? If you've ever worked with them, they love to die. But especially after a night drinking, right? So, but maybe tonight. So right here, you can actually see we did a culture on a standard Petri dish system and on our PZT, and we saw that the viability on PZT was actually just as good as in a standard culture medium. So the lead, I guess, doesn't leak out of the PZT. We can actually grow them just fine on there. You can see the action potential is perfectly fine in these neurons grown on the PZT system here. So then we measured it here. You can see this amazing result that we got where we put down this patch clamp probe on the ribbon. We depolarized the cells, and you can see every time we depolarize the cells here, we got this spike in the PZT response. So here's it blown up. We get this perfect AC spike here in our piezo response here every time we spike those neurons. Okay, so we are actually able to measure with this sensitive cantilever system. This paper is under review right now in Nature Nano. We're able to measure this this flexoelectric response in the cell using this piezo system. And so the last thing I want to show you here is that we can go back and we can actually quantify exactly how much these cells are deforming on the ribbons. So you can take a probe here, it's just a standard AFM probe, and push down on the ribbon. And if you use different tips with different stiffnesses, different spring constants, then you can basically map out a profile of the force that you apply compared to the PZT signal that you get, the response. And then you can then go back and measure how if you apply different polarizations on the cell to see also what your different PZT response is here. So you can actually quantitatively determine the force and the deflection that you're impeding on the ribbon. This is my last slide, don't worry. Impeding on the ribbon by the cell. And we can actually distinguish that it's down to a force of about 2 nanonewton and a deflection of about a nanometer, which agrees almost perfectly with the AFM data that we got before. So we can actually use these ribbons, because it's PCT, high piezoelectric charge constant, very sensitive, to actually go and probe at the nanometer scale mechanical deflections in neurons, which we thought was cool. Okay? So this is the group. This is my group. I'd like to thank them. We don't have a big group, but we have a very feisty group. And basically, to point out a few people, Than is the one that did all the neuron stuff and the pencil approach. Kelly is the one who did the automated microfluidic phage system. Let's see. Manu is the guy who did all the bacteria sensing on the tooth before. And I'd also like to thank our collaborators, Rajesh Naik, who helped us a lot with the peptide work. He's at AFRL. Prashant, who did all the modeling for us, professor at UPenn. Fio Almanetto, who gave us the silk. Naveen Verma, who helped us with the wireless coil. He's a professor of electrical engineering at Princeton. And our funding, which you can see up there. Okay? So thanks a lot, and I'd be happy to take any questions.
Great. Very interesting.
Thanks.
Nice work. And a lot of it.
Yep.
Is your female student there over 12 years old?
As of last year, yeah. Sure.
Okay, we have some questions.
Any questions? Yeah.
So how thick is your PZT membrane?
The ribbon?
The ribbon.
It's about 100 nanometers thick.
Can you make it even thinner, and how does that affect the response?
It's hard to make it thinner because basically you have to anneal these things, and so you need to have enough thickness that when you anneal it, you can form the perovskite structure. And so we've had difficulty because we're doing sputtering, not MBE. And so we need to have it be thick enough that you can actually get a reasonable annealing so you don't crack the entire ribbon during that. Because there's actually a small lattice mismatch with magnesium oxide. There's no perfect lattice match with PZT. Yeah, so we 100 nanometer seems to be our working point. Yeah. We can do thinner, of course, but yeah.
There's a question over here.
When you put the peptides down on the graphene and attach it to the edge, is there any selectivity? And what kind of edge around the chirality at the edges is that?
That's a good question. So if I had to guess, okay, so I'm going to answer your question and then broaden it. So basically the answer to that question is probably no in this case, because these are actually more electrostatic interactions. But your question raises an extremely interesting point, which is basically you can actually change the chirality of amino acids. There's D amino acids and L amino acids. And they have different chiralities. And so your nose can actually distinguish racemic molecules, which are molecules which are stereoisomeric, right? And no one knows exactly how that's done. But if you can create a sensor that can distinguish one racemic molecule from another, that would be incredibly interesting. Because in fact, racemic molecules can have completely different chemistries. There's actually some drugs where the R version is functional and then the S one is not. So the pharmaceutical industry spends a lot of time. Some of these like high potent drugs are actually ones where they just cut out the racemic component, kept the other one. So it's a big problem. It's an interesting problem if one could actually, I don't know if peptides could do it, but it'd be cool if they could actually distinguish racemic molecules somehow.
Okay, we had a question.
Yeah, I was wondering, as far as like putting graphene in people's bodies, is there a lot of research on if it's safe to breathe graphene and eat graphene and have it like in your blood?
Yeah. I don't know. I'm going to have graphene for dinner tonight, so I'll let you know. But so someone asked me this question. You know, can you put it on a tooth? Oddly, I'll send you this if you don't believe me. I did some research, and there was the dental industry wants to put graphene on your tooth to protect it from bacteria somehow. I actually read this somewhere, believe it or not. So, you know, but I'm sure it's something, it's obviously the contamination of any nanomaterial is something that people have to look into more carefully. So, yeah.
So was there a special reason to choose neuron over other cells?
Yeah. So that's a good question, and the answer is it doesn't matter because they all have this kind of tight bilayer. But we thought it would be interesting to do it in neurons specifically, and but in fact it doesn't. Your point is important because we found with our modeling that you don't need an action potential. None of those spikes were actually action potentials. You don't need to have an action potential in order to get this response. Okay. In fact, you don't even need to have ions crossing the membrane. All you need is a redistribution of ions inside and outside the cell in order to see this.
Coupling.
Exactly. Yeah, that's exactly right. Yeah.
So let me just inject a question here. You
Sure.
showed in your first video this system was sensitive to single bacterium. Is it sensitive to the type of bacterium, or was it just any generic bacterium?
Not on its own, not without any peptide or antibody on there. It's not going to be able to distinguish on its own at all. I could be wrong about that, but I don't think so.
So any bacterium.
But as a
is that a capacitive thing again?
okay, so yeah, so as a corollary to what I just said, you know, there's two different types of bacteria generally. There's actually gram-positive, gram-negative, and they actually have different cell wall structures. The gram-negative is more negatively charged, so that should actually have a larger, because this is all a gating effect. It's a capacitive effect, but it's a gating in a transistor geometry, so it's like a gate effect. And so I would think that a gram-negative bacteria would have a larger response than gram-positive, just because it's more negatively charged than gram-positive. Yeah.
DNS mechanism has a challenge for making like PCB nanowires, but is it possible to use a top-down approach like a etching or something?
That's exactly what we
You
did.
better repeat that question.
Oh, he wanted to know whether we could use a top-down approach to make PCT nanowires. In fact, that's exactly what we did here. That's exactly the approach we took. We started with films and carved them up. And even now, I can't think of another way to do that. I take that back. We are working on a project. The 12-year-old girl is working on a project now where we're trying to get around that problem. So.